As they say in Japanese, Ohayo gozaimasu, meaning good morning. Welcome to Making Stuff with Chris DeHut. Today we're going to take a look at momentary switches and how they interface with the Raspberry Pi Pico. What we will cover today is what they are, where they are used, we'll review a datasheet, we'll take a look at a Fritzing wiring diagram so that we can see how to connect one to the Raspberry Pi Pico, and then we're going to take a look at how to use them 6 different ways using behavioral programming, everywhere from a simple push-button operation to making it mimic the function of a toggle switch. Momentary switches are really amazing devices. These simple switches have been used on just about everything over the years, and they've replaced a lot of other forms of switches. Its operation is very simple. You push it, it's on. You let go, it's off. As simple as can be. The mechanics of them can be anywhere from a mechanical device such as this one or a membrane type switch. These types of switches can also mimic the behavior of other types of switches, and we'll be talking about that quite a bit as this video progresses. To begin, let's take a look at a couple of momentary switches. This is your basic tactile switch type device. You'll see these in a lot of kits and so forth. You can buy these components. Here's one without the cap, one with the cap. And they're great for mounting on circuit boards, as you can see. Another type is this style, which is the type we'll be using as our test bed here in the video. It's a panel mount. These come in a variety of styles. Here's a cool looking security style, vandal-proof, metallized, or it's fully metal, but the function is exactly the same. This one's got screw terminals for wire mount. Here's a square one, same function, push it on, release it off. Panel mount with a screw and a couple of solder lugs on the bottom. Here's another one. This one is more of an industrial style switch. You'll see these used a lot on industrial controls, primarily dating back more so in the 90s, maybe 80s even, but the 90s and early 2000s. A lot of this style switch is also being replaced by membrane switches and more economical choices. While preparing for this story, I thought I'd get some photographs of industrial controls, because there you'll see an awful lot of high durability type controls, switches, and devices that we often talk about in this video series. This particular one here is an air dryer, which takes compressed air, dries or removes the moisture from it. On this one, it's using membrane keys, and you'll see that we've got 1, 2, 3, 4 momentary buttons on that device. Here is a very old Ingersoll Rand air compressor control. Well, I say very old relative to today. This is probably a 1990s vintage. This is using 1, 2, 3, 4, 5, 6, 7, 8 momentary switches to perform various functions on it. This is a modern day air compressor, and this one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 momentary switches on this one. This is a 1970s vintage industrial CNC control. Oddly enough, this is one of the controls that I learned CNC programming on back in the very late 70s, early 80s. This particular control, even as being as old as it is, has 33 momentary buttons on its operator panel. And one thing you'll notice here, and I want to bring this up specifically, another thing that was common in this vintage of CNC control would be toggle switches. Those would have been a strong carryover from the 40s, 50s, 60s, 70s into the 80s and almost into the 90s before they started disappearing a lot off of industrial controls, being replaced by momentary switches. Now this is a very modern CNC control. This one is essentially brand new. It's 2022, and in my count up, I'm not even counting these keys here. I'm just focusing on the QWERTY keyboard that's on it, all the numeric functions, the screen selections, the conditional state buttons, and all this stuff. And that particular control on its operator panel has 118 momentary switches on it. Now, the ones that I'd just like to quickly point out, these four and this particular one on that older control would have been toggle switches. So here you can see how they're replacing a toggle switch. Notice they have an LED indicator so you know which state it's in. Car dashboards. Here we can see a modern car. This is an Infiniti. This has 52 momentary push buttons here in view. 52 of them in that small area, just to control your climate, your navigation system, your clock, and your radio, and to start and stop the engine. Now, here's something where you should be very familiar with regard to momentary switches. There's 110 of them on this particular style of keyboard, and I'm quite certain you've seen this before. This little keyboard has 82 push button switches. I use this one for one of the computers here on the electronics bench. You've seen calculators, you've seen remote controls, small ones, and remote controls that are a little bit bigger. And of course, you've seen the full-on remote controls that use to control everything from TVs, VCRs, well, you might not know what those are, DVD players, DVRs, etc. So momentary switches are literally all over our lives. They're in all sorts of appliances, devices that we use. Anything that's electronic most probably has a momentary switch on it. Even, I think, still Apple phones still have a momentary switch on them. Most of it's replaced by touch screens today, but nonetheless, you'll see them a lot. This particular data sheet is not referencing the switch that I'm going to be showing you. The switch that I'm showing you, I picked up off of eBay or Amazon, I forget where. Bought them in bulk. They didn't come with a data sheet, but they do have markings on them to show what their max voltage and current rating is. But this one that I'm showing you here is a very common data sheet for switches. They don't provide a lot of data. They're going to show you the action, hole patterns, how close you can have them together if you're putting multiples on a panel, the mounting hole diameter. They provide a lot of good mechanical information. But the one that you really want to pay attention to, and in our case working with microcontrollers, is not really that important, but it's just good practice. Your electric rating or electrical rating for the switch. Ideally, you want the switch to be able to easily handle the current and voltage that you're going to put into it or put through it. Now, in our case, literally, we're dealing with milliamps, very, very tiny amounts of current, and typically on say a Raspberry Pi Pico or a Raspberry Pi, even an Arduino at 5 volts, we're at 5 volts or less. So almost all switches can handle that. But nonetheless, you should always check to make sure that your switch can handle the voltage and current you're going to use it with. Another thing is mechanical lifetime. 2 million operations. Anything that we would make is probably going to certainly die or we give up on it before it's got 2 million operations in it. But if you're building a project for long-term use, you do want a good quality switch that has a very good life cycle to it. There are a couple of different ways to wire up switches, and one of the most typical ways that are easy for everybody to understand is when we hit the switch, we're applying voltage to something. We turn on a light, we are giving or allowing voltage and current to pass through the switch and turn on the light. So in the case of microcontrollers, the easiest concept to understand is that same concept. When we push the button, our input signal is going to go high because it's being provided with voltage and current. Now we can also do that the exact opposite way, but it tends to confuse a lot of people. So our focus will be on using the switch to provide voltage to an input. And that'll also apply when we get into the program in a few minutes. But here we're looking at a Fritzing diagram. This is our 3.3 output of the Raspberry Pi Pico. I bring that around to my positive rail on the breadboard. I connect that positive rail with the 3.3 volts into one side of the switch. When you press the switch, the contacts close and allow that voltage and current to pass through the yellow wire, in this case, into GP input number 15, which is what we're using. Of course, you could use any of the general purpose input or output pins that you would like to. In our examples, we're working with pin 15. Now we'll take a look at this on the breadboard. On the breadboard, here you can see our 3.3 volts out going to the positive rail. Along that, the blue wire goes into the momentary switch. Signal comes out on the yellow wire, goes into pin 15. And then operation is very simple. Just press the button and release it. So as you can see, the breadboard is exactly like the Fritzing diagram. It is really quite straightforward. So now that you have an understanding of what a momentary switch is, where they're used, as you could see, in many applications, how they're wired up, I think it's now time we should start looking at how to make that switch behave the way we want it to. For our first program, we're going to look at how not to do things. We'll just follow along and then we'll refine this with good behaviors for momentary switches. The first thing we're going to do is load in the machine library, and that is a library that is specific to the Raspberry Pi Pico, and it allows MicroPython to communicate with the hardware on the Raspberry Pi Pico. UTime is a MicroPython version of the time module found in normal Python. We're going to use that for sleep and other time-related functions. Getting into the meat of things, the first thing we're going to do is create an LED object. And that object is, in essence, going to be this LED that's on the Pi Pico. And we'll use that as an indicator light for a few of these examples. And to create that object, we're going to use the machine library's pin method. And we're going to assign that to pin 25, which is the onboard LED, and we're going to assign that pin as an output. So when we set that value to on, the LED would come on, and if we set the LED's value to off, the LED would go off. Next up, we're going to create an object for our actual momentary switch. And we're going to call it Momentary Switch, and that is using the machine.pin function, and that's attached to GP number 15. We're going to set that pin as an input using IN, and then we're going to use machine.pin.pullDown. Pull down is a very important function, and you should never forget to use this unless you're using a hardware pull-down resistor. But we go to the circuit board to understand that. Here is our 3.3 volts coming to the rail, and then in this blue wire, we're good at 3.3 volts up to the switch. The yellow wire coming out of the switch and going into GP number 15 has no voltage in it. So GP15 could either be at any volt, it could be at 0 volts, or it could be at 3.3 volts. It's in a state of what we call floating. We have no idea what it specifically is, but what we really want it to be is at 0 volts. Now there's two ways we can do that. We can add a resistor at this point to pull that circuit or that input down to 0 volts. So we would add a very high ohm resistor, maybe a 10K ohm resistor, and connect that to the ground rail, and that would keep this signal at 0 volts until the 3.3 volts is allowed to pass through when we press the button. And then that would pull that signal up or on. Here in the software, we have a function within the Pi Pico that has a built-in pull-down resistor, and that is its purpose here. We're pulling that signal on pin 15 to 0 volts, and that will help make sure we don't get any false readings. Remember, we just don't want the pin floating, and that's the state that it would be in without this pull down to 0 volts. Next up, we're going to go into the polling method of handling an input. Now, there are other alternatives. You could use interrupts to handle switch inputs, and that's very effective for something that you need to respond to in microseconds of timing. The problem is they are so fast, they will create additional problems that you don't want to deal with, and that problem is called switch bounce. If you're not familiar with switch bounce, the best way I can explain it is to show you what electronic signals look like from an oscilloscope. This is an example of a very good square wave signal, and that's at 1,000 hertz, 1,000 times a second, so we're looking at a very, very, very small period of time. This period of time from here to here is 250 microseconds. Very short period of time. But what this oscilloscope allows us to do is look at that time in fine detail. This down here is 0 volts. This up here is 3.3 volts. So voltage is up and down on the scale. Left to right is time. Well, we couldn't see this by looking at an LED flashing on and off at less than a millisecond. And that's the purpose of an oscilloscope, to measure things that we can't see or interpret directly. But you'll notice that at the off, signal is flat. When the signal goes high, kind of think of this as turning the switch on and we got voltage going into it, and it goes high. And then here we're at 3.3 volts all the way across. And then the switch turns off. And now we're at 0 volts again. And that is a very beautiful square wave. There's a little bit of noise in it here and here, and that's not to not be unexpected with simple wiring like we've got here. Now, the important thing to notice is this area right here. When we go up, then it makes the right turn at 3.3 volts and pretty well stays stable there, give or take. A very, very small voltage change. Now let's take a look at switch bounce. And here we're going to see two signals on this diagram. Just ignore the purple one for now. This is, again, essentially close to the same time base. This is 100 microseconds, a very, very short period of time. One for the distance from this group of lines to this dotted lines. And here we see voltage again going up and down, 0 volts here, 3.3 volts up. What I want you to look at is this. Here is a switch turning on, and this is, in fact, the switch that we're going to be using. You'll see it go up. It stays high for a very brief, very, very brief couple of microseconds. The switch goes back to 0 volts, and then right back up to 3.3 volts. That is switch bounce, and that is common in almost all mechanical switches. When you turn it on or turn it off by pressing it or flipping the toggle switch, you will get these intermittent on-offs for a very brief period of time. In this case, from here to here would be, let's see, that's 20, about 40 microseconds that happened. And that isn't bad. You can get much worse than that, and it can ring for a while further, but our concern is we can't let it go down. Unfortunately, we can't control that, so we've got to deal with that in software. Needless to say, there's capacitor, resistor circuits that can deal with this mechanically, but it gets way beyond the scope of this conversation. So just be aware that when you turn a switch on, in your mind you think you turn it on and it stays on until you turn it off. Well, it's actually bouncing, going on and off, possibly a few times within the first few microseconds. Back to our program. So the way we're going to get around that is to not use an interrupt, because they don't deal with that bounce very well because they're so fast. What we're going to use is a very common method called polling. And polling is we check that switch every time as we pass through a loop. And that's what we've got set up here. MicroPython programs, as with almost all microcontroller programs, have an endless loop. That's called your main loop in your program. Very, very typical. In this main loop, I'm going to look at that switch and see which state it's in. Very simply, if our momentary switch, the object that we created for pin 15, if it's true, meaning it's on, I'm going to turn on the LED and by setting its value to 1. And then we'll print button is pressed. Then I'm going to continue that decision-making process. If the momentary switch value is equal to false, meaning there's no current going through it and it is being pulled down by that condition right there, that pull-down resistor, we'll turn the LED off, and then from there we're going to go into just a quick sleep of about 10 milliseconds. And that's just to mimic other work that would be done in your main loop. Obviously, your program is going to do more than just look at a switch and determine if it's on or off. Most probably going to have some other actions. Now, this would seem pretty logical, right? We're going to check to see if the switch is on or see if it's off. Let's see how that runs when we go to run it here. Oh boy, I got a bunch of button is not pressed, which it's not. You can see here. Now I'm going to press the button, and you'll see it just keeps repeating. I let go of the button, repeats. It's constantly running and constantly printing, and it's just a mess. How do we deal with that? Because if we were to perform an action based on this condition, we're going to get that same action to repeat really fast and an awful lot. So this isn't generally what people want to do with a momentary switch. So from here, this sets our baseline on how to get rid of this behavior and make it behave more familiar to push-button switches that we use everywhere. For our second example, we're going to address the key repeat issue that we're seeing that was, for the most part, basically uncontrollable. It just was very bad behavior. So what this particular program will do, it will still be a polling operation, and we're working with comparisons to the previous state of the switch to prevent key bounce, false reports, as well as automatic repeats. So this one I've labeled actually as a good example to perform action on the press of a button. And that word press is highlighted there because that'll be discussed further down in the program between this example and the next one. Coming down, the new thing that we've got here is I've changed the name of the button. It's now the down button. That'll help us to differentiate the next 4 or 5 example programs. So the down button is basically the same, our switch that we created before, just a different name. I also created a variable to hold its last state. That is, I'm going to call it the magic to help us do what we want to do and get behavior that's meaningful to us. And I call that the down button previous state. And I initialize it by setting it to the value, the current value or the current state of the switch, which is highlighted right here. I'm going to turn on my mouse highlighter here because sometimes that makes it a little easier for you guys to follow along. We'll jump right down to our loop. Pretty much that's exactly the same, except for I've changed the name of the handler to be the down button handler, as I did up here. I've added a global down button previous state so that I can access it in the main program and in the sub function here, because I will be reading and writing to that in this routine. Now, here's what we need to discuss first. What we want to do is only react to the button being down if it wasn't already down. So if the button is down, I don't want to do anything, right? Because then it repeats uncontrollably. So the only way I can differentiate between that condition and how we want it, meaning that if I press the button, the only time that button should react is if it wasn't already on, thereby negating the repeat. And that's what this conditional statement does here. Now let's look at the second half first. The down button previous state is equal to false, meaning right now nobody's pushing on it, the switch is not touched. Now at the beginning of it, we look at the actual switch value, down button dot value, is true. So somebody pressed it and it was not on, therefore we're going to perform an action. And in this case, we're going to, very first thing we must do is update our previous state variable so that it is set to what is now the current state. And then I'm going to print it so we can see it down below. And then this is the area where you would put your code to do whatever action you want to occur. Now, we need to also reset this, even if we're not acting on it, but the inverse to this condition, in order to reset our down button previous state, is such. We want to do this if the down button previous state is true, meaning I was holding it down, and then I released it, meaning it is now false. The state changed from being pressed to released. Now I need to update the previous button or previous state of the button so that the next time through the loop it can react and respond accordingly. Let's see what that behavior looks like. All right, I'm going to push the switch, and all it did was give us one action. I released the switch and nothing else happened. So I'll press the button again, one action, release, nothing. I hold it in, no repeating. Let go of it, nothing happens. I can press it quickly, kind of like you do on a keyboard if you're a fast typer, and we get the repeat that way. So this is a very good example of how to work with a momentary push button. And its response, or the action that will occur, is when you press the button. That's the important thing to remember for this example. As the button goes down, or the condition electrical signal goes high, at the moment we press on it, then we're going to get our true state and our action. Now the important thing to remember with this one is that press of a button. So as the voltage goes high, or the signal goes high, by the action of pressing the button, we want to perform our action. Now there's an opposite to this function as well, and we'll demonstrate that in a moment here in example number 3. Example number 3 is going to perform its action at the release of a button. And you might be wondering, well, what's the difference there? Well, it's very different. For example, I'm going to switch to a tab here, and I'm going to press and hold the mouse button. So I press, and I'm holding, and it switched right away to the screen, right? I'll do that again. I'm going to press and immediately switch to this tab. Now let's go over to the stop-start button. I'm going to press and hold. Nothing's happening. Nothing is happening. I'm going to release the button, and boom, something happens. That is the difference between acting on the press of the button or acting on the release of the button. Now our program for this is very much the same as it was earlier. We've changed things to now up button instead of down button. Changed our variable to up button previous state. This is where you'll see the code difference. Essentially, our action code was up here on the previous example and down here for this example. And this is where we're going to be releasing. This is the release detector, so to speak. So we'll go ahead and I'm going to press that. And now we're running. I'll press my button. Nothing. I'm holding the button in. I release the button, and now the action occurs. Press, nothing, release, we have action. So there is the difference between example number 2 and example number 3. And they have purposes for both. I mean, it depends on how you want your software to behave for the end user. So that'll wrap up are very basic operations that are very reliable and useful. Now what we're going to do is create a behavior like a repeating key on a keyboard. The process isn't too bad. We're going to start out with our usual stuff. I've now changed our objects to the name of repeat button so that we can keep track of which program we're looking at and working on. Our main loop is the same as before. But the real workhorse here is always our handler function. And in here, we're going to get started with the very first decision, and that's to see if the button is already pressed, to do nothing. If it's not pressed, then we're going to do something, just as we have been before. And that prevents re-entrance or key bounce and some other miscellaneous little problems. So once that happens, we set our previous state to true because now the button is held down, and we'll print start repeater. Now you could insert in this area right here the first action you want to occur. Be it whatever. In our case, it'd be like if we were doing a key repeat, we would print the key, the letter. And we're going to sleep here 300 milliseconds, because after the first one, you want to give the user an opportunity to release it so it only repeats once. However, if they're holding it down while repeat button value equals true, the button is being held down, now we're into that repeat loop. And it'll continue to do this until the user releases the button. During that time, we're going to print the word repeating to simulate doing some actual work. You would put your real code in there. And now we're just going to sleep for about 50 milliseconds. And in this case, you would adjust these to suit your needs and your application. When you let go of the button, now at that point, our previous state will switch from true, as we set it up here, to false, and then the whole process stops. So it's really quite simple to implement and use, and we'll show a simple run of that function. Here we see nothing's going on. I'm going to press the button, and all of a sudden it takes off repeating. Let go of the button, and it stops repeating. And it's kind of hard to see. I'll even set it up a little higher so that maybe it's a little more pronounced. Let's go to 600 milliseconds on that first delay. Okay. I'll press it, then it repeats. Now you can clearly see that delay before we go into the remaining repeats. And if you're quick, you can press your button once and you don't get any additional repeats. So that's how you work with a repeating key handler that we've set up here. Another similar function that you might want would be something for perhaps a motion control device where you're going to press a button, hold it on while something continues to move. A motor runs or a servo continues to move, and then you let off the button and then it stops moving. If you're working on a game design, which you can do with microcontrollers, if you're working on a game design, this might be you press the button and one of your characters moves until you release it. Or it could be any other type of object. The implementation of this is really very similar to our repeat function, but the difference being in our key repeat function, there would be a distinct hesitation between each of the repeats. In this case, the intention is you press the button, the thing stays running until you release the button. Let's take a look at the code. It's really quite simple. Our beginning is all the same, all the way up to our condition right here. All that is essentially equivalent to any of our other examples. Here's where we press the button, we update our previous state. We're printing out start the jogging as a flag so I can monitor it down here. But we'll turn on the LED, and that LED will stay on until I release the key, and that is release the button. And that is what this part of the code will do. As soon as I release the button, the previous state will be set back to false, which it should be. We'll print stop jogging, and then we'll do our actual work, and that is to turn off the LED. We'll see that in action here. I'll press it, and what we'll see is the LED in this area come on. I press, hold, the LED is on. That would be your character moving or motion happening. Release the button, and it turns off. And that can be repeated, held as long as you want or as short as you want, etc. So very quick, simple behavior that you can add with a simple momentary switch. Now this next one is a bit more involved, but nonetheless it's a very common one, and I alluded to this when we were talking about the industrial controls earlier. Older devices utilize toggle switches to set a state on or off. And often in your code you would reference that state. Is it on or is it off? You wouldn't be concerned about the transition from on to off or off to on. More so when you're going to do something that state affects, you would check to see if it's on or off. And that's what we're going to replicate with a momentary switch. We're going to make it behave like a toggle switch or a rocker switch or even a latching switch, slide switch, anything that holds its state. Now, I will caution you on this. This is a great technique. It's used all over the place. That momentary switches are used when you want to set a condition to one or two states. But you need to provide feedback. A rocker switch, a slide switch, a toggle switch. These are all devices that you can look at it mechanically, the device itself, and determine whether it's on or off. We need to provide feedback to the user of that condition, and we'll use our LED on the Pico. Of course, you could use another LED, a discrete one, as well. It's just a way of communicating what state we're on. So let's take a look at the code. Now in code, usually what you're doing is looking at the state that the switch is in, not necessarily that transition from off to on. So that's what we'll focus on with our code, is to see what state it's in, not the transition like we have been doing with the momentary switch. But the other thing that this switch does very effectively and simply is it tells the user which state it's in. Off being down, up being on, and you'd usually label it off and on. A rocker switch can do the exact same thing, easily communicate to the user off and on. Well, with a momentary switch, you don't have that ability. So what we have to do is use another device to communicate the on and off state. And for that, we're going to use an LED. On the industrial controls I showed you earlier, the very old one, the FANUC control, used 5 toggle switches, and you could tell which one was on and which one was off by looking at it. On the more modern control, I pointed out those same 5 functional switches, but they had an LED to indicate whether they were on or off. So here in our code, what we're going to do, I've changed our toggle or our LED to a toggle indicator LED so that we know which state we're going to be in to the user as they're using it. That's our communication device. We're going to create a couple of variables for the toggle switch itself, or the toggle function. We're going to start with the toggle state being set to false, off, and we're going to set the toggle indicator value to off. We've got our function and the related objects renamed to toggle switch all through our code here. Our main loop is the same, but we're calling now the toggle button handler, which is our function. In this area here, we're doing just as we've done before, comparing the current state of the momentary switch against its previous state. And based on the true-false condition, we know that we can enter this as the first time through this loop, and we don't get the repeats. We'll set our previous state to true. Then the real trick is in this area right here, where if the toggle state, meaning the up here toggle state, we're calling it our toggle switch state, if that was false, turn it on. So we'll set the toggle state to on, or true. If the toggle state was true, we now need to turn it off. And so we'll set the toggle state to off. And then to provide feedback to the user, we're going to turn the LED on to equal whatever state we just set here, so that the LED will follow the actual variable toggle state. Now, elsewhere in your program, when you're trying to determine or decide to perform an action based on that toggle state, you would compare against that variable. And that's how you would know that the switch is on or off, and make a decision based on if it is on or off. Now back up here, this is happening while we press the switch, and we had to perform this action to get the condition set correctly for our variable. But when we release the momentary switch, which is tested by this condition, we will set the momentary switch state, previous state, back to false. That operation, this line and these lines are just like we've done in many of the previous examples. So nothing really different there. The primary difference is this area here. This is the actual action caused when we press that momentary switch. Now let's see that in action. I pressed the button and released it. The LED is on, indicating that that particular state was turned on. I'll press it and release it, and the LED goes off. And with that, we are mimicking the behavior of a toggle switch, a rocker switch, or any other type of latching switch. We've got feedback, etc. Now keep in mind, as mentioned before, we don't have to worry about using that particular LED. It could be a discrete LED that could be remotely located on a panel somewhere, ideally right next to the button. And if I didn't mention earlier, I do want to point out that all the source code, the Fritzing diagram, etc., are available on our companion website, and there is a link down below in the comments. Now, I would like to apologize. I knew this was going to be a rather lengthy video, but I think it went really long. But I feel that covering all these different behaviors gives you much greater capability when just working with momentary switches. They can do so much more if you just apply a little bit of creativity in your programming to accomplish more with them. So I'm going to wrap it up at this point. I really appreciate you taking the time and spending it with me today to go over these momentary switches and the coding. And if you enjoyed this video, learned something from it, or liked it, I sure would appreciate it if you would subscribe and give us a like if you enjoyed it. And with that, I'm going to look forward to seeing you in the next video. At least I sure hope so. Thanks again.